Thank you very much. Actually, a bit too loud. I will speak in non-commutative algebras. One can speak about modulus, various modulus space, like modulus space of non-commutative space, and there are interesting Toposes. But I will speak about some kind of very ill-defined vision uses non-commutative space as topology itself. And can speak about Lagrangian. And for example, if we have some object like modulo, how can we say it's somewhere is zero, somewhere is non-zero? Just very basic question. So I will start with some, next slide will start with some strange example from analysis. You'll see it's pretty recent result. This for me was very surprising. And which is the following. You consider the Schwarz space of R, smooth functions which rapidly, more faster than polynomial decay into together small derivatives, also all derivatives should decay faster than any power coordinate. So we have one of Schwarz space, it's an invariant on the Fourier transform. And you map this Schwarz space to space of functions on some countable set, which is generally of two copies of sets of roots of natural numbers, positive and negative roots. And you map this voluntary, you map the function to various roots of natural numbers, all Fourier transform, where is the Fourier transform? And this roots of natural numbers. And the claim is that this map identifies it's essentially isomorphism. You have just one identity for the image, which is called Poisson summation formula. You take some values of integers, a function of Fourier transform, the same number, and of course each integer is the square root of its square, so it's part of the data. And the claim is only one constraint, so you put out hyperplane, codimensional subspace in space of functions of this countable set, decaying faster than any element, which makes sense. Then I get a projection. Actually, people, it's kind of strange fact. They also, Raj and Kazovsky, they propose explicit formula how to reconstruct function of this values using some model forms. There was some kind of very rough realization. People thought that like signal processing in such kind of equations. You can see the values of function some set, but values of Fourier transform another set. And if sets have some polynomial density, and indeed two constants, because it's like instead of square roots, consider some bars. There are kind of two regimes. If some of the densities, this number is less one, we have a very dense set of data, then you can reconstruct them uniquely, and if it's strictly bigger than one, you can reconstruct. And in between this kind of intermediate regions, that is remarkable things. So there is a similar effect, it's called Z transform, it's called Z transform. You can parameterize functional Schwarz space in functions on this set in a different way. Namely, you consider integrals with function with circles depending on integer parameters. So you consider shifted exponents and also Gaussian and multiplicative imaginary exponent. And then again you have your Schwarz space of functions with faster than polynomial decay now on a two-dimensional set. And you claim that they identify Schwarz space is a codimensional space, one can easily write the equation itself, see the function. Okay, so there are two facts. So we get this square roots of sets of square roots of pairs of integers. Can we understand them simultaneously? And I thought we can follow creativity and discuss this. People thought that's really a good idea. Very, very basic. The following how to understand what is going on. So here we have exponents of functions which decay to infinity, so the sleeping charge with a real part less than 0. These are different decaying functions. And you consider such functions up to rescaling, multiplication when non-zero complex constant. And they claim that this function sin 1 corresponds to this ellipsis in R2 of, let's say, of area 1. And it's invariant with respect to action of symplectic group and symplectic appendix summation, which we mentioned on short space. So we can prove various ellipses, what they call several ellipses of area 1. But this ellipsis can be very, very thin along. And in the elliptic case, when it's not, you get lines. And lines correspond to limiting to non-smooth function to distributions, like delta function will be vertical line, and or exponent implies it will be horizontal line. And what is the picture? So in the first equation, we pair our smooth function with distributions, which are lines, and lines distributed kind of two ways, horizontal and vertical in this way, distributed with square root density, or quadratic density, and in other picture I have essentially little sphere pattern on R2. So previous one say organic, one is integer vertices. And what is similar in this picture? You start to draw very big domains, such that length of the boundary is very small relative to the boundary to the area of domains. And then you can, in this kind of optimal case, you can find large domains such that now this ellipsis or elliptic ellipsis in the center domain grows with constant 1 times the area. And the constant 1 is really optimal. Yeah, so this leads natural suggestion to get not horizontal vertical lines, but lines in other direction. It also gives some sort of geometric prediction then we can expect isomorphism. Yeah, so the right picture is what people, quantum mechanics usually consider. They call this things coherent states, and they state that you have symplectic manifolds, it's R2, and you have some domain of R2, it's roughly gives a hyperspace dimension to the area. Okay, so for a moment this picture will be not used, but later I will jump to this picture. Yeah, so what about non-commutative algebra? So if you have, when general say about supports, on a manifold you can have kind of basic function in various incarnation. Yeah, if you have some object on a manifold, then usually people consider supports a closed subset of your manifold without great variety, smooth manifold. There is a final notion, it's micro-local support. It was discovered by Schwarz and Schubera, which is Schiff's theoretic version. It's subset of the Lagrangian part. And the Lagrangian bundle is a symplectic manifold. It has non-degenerate closed form. So the support actually is defined in some interesting way. So what you use here is like for real manifolds. You mentioned for each point to consider locally half spaces. You identify neighborhood of one and vector space, consider half spaces, and consider behavior of shift with respect to this half spaces, and that gives you an actual subset and phonical subset of the Lagrangian bundle. Yeah, so something intellectually not satisfactory in this definition. For example, the Schwarz asked the manifold to be C1, and there are many indications, like this question symplectic geometry are more rough, with piecewise linear symplectic manifold. And from point of view of what's going on with shifts, it's really interesting question because to think about supporting a more general situation and try to address potential harmony in more rough picture. Yeah, so the usual support of non-trivial object would be arbitrary small. It's not empty, it should be not empty, non-zero object should be not empty, it would be point. Macro support is always at least n-dimensional and n is dimension of your manifold. And moreover, it's called coisotropic. So in the situation where this, let's say, contains a big part which is smooth and analytic, then the tangent space containing smooth point contains a Lagrangian subspace. So it's at least one-dimensional. And micro support are conical long fibers of projection. So in tangent bubbles on which tangent space you get conical subset. And when you have a situation with small parameter, then I will get one no longer conical subset. Okay, so what are examples of functions, objects, and supports? Yeah, first in real analysis, it was Fermat's theory of reoperators. Now consider real singularity manifolds. And consider something like oscillating functions, functions which exponent of I as real function divided by small parameter r. And such things you can kind of go easily from smooth functions to distributions, and such we have correspond to Lagrangian submanifolds in the tangent bundle. Now, for this function, we will have a graph differential function, but then Lagrangian manifold is not graph differential, their distribution. Yeah, and yeah, so it's a nice geometric way to think about distributions. And very often, distributions are kind of nice functions that satisfy at least a representation theory of which is called Lagrangian. This is like a holonomic system of linear differential equations. Let's say this polynomial coefficients. And then I'll get d-module of a complex algebraic variety. You write differential equations real coefficients, but you can stack everything to get complex d-module. And then micro support is a complex algebraic Lagrangian subvariety. And then again, you have now complex numbers. In the case of regular singularities, you have Riemann-Hilbert correspondence, and one can associate with holonomic d-modules regular singularity, reverse constructible shift on your variety, and which you also apply this theory of macro support for shift, absolute shifts, and you get the same subset. And finally, this regular d-modules, they appear as Gauss-Mann, at least in Gauss-Mann connections, appear algebraically in normalization, and there are with other normalization, analytic shifts, and now we can consider analytic shifts in finite characteristic, and then finally we get back to functions, because we can consider points over extensions, arbitrary extensions to your finite field, and by taking trace properties you get actual Q-bar value functions. Yeah, so there are various pictures of functions of varieties of different types. Yeah, so it's what's called dimensional support and holonomic models. Yeah, so let's start with commutative case. So suppose we have finite generation commutative multiple field, so it's just some great variety in finite space. Then someone has polynomial growth. If you choose any set of finite set of generators, and let's see the subspaces given by problems of upland generators. Then I get increased exhaustive integration, and the dimension grows polynomial as exponent is a full dimension of algebra, dimensional spectrum. And if you have finite generated modules, such algebra, you can define or calculate dimensional support with the same way. You just choose arbitrary number of final generators. You choose generators of algebra and make this iteration. This is the exponent. Now, if you have a variety of smooth affine variety of subfield, then we get algebra differential operators. And it's finitely generated, and its dimension, with is 2n. And the classical fact, which actually goes to, I think, the thesis of Joseph Bernstein, is that if you feel the probabilistic 0, then dimensions of finitely changing models cannot be small. They always lie between n and 12. And the models whose dimension support is exactly then are called holonomic. In analysis, this concept kind of like maximal system of n equations and variables. So this definition of the models is not really canonical definition, except in the case of affine space. In the case of affine space, algebra differential operators has certain generators which and relations written here, which invariant of the symplectic group, and we have integration, social integration also invariant of the symplectic group. It's called Bernstein integration, and Strong is raised by this products of monomers of total degree plus n. And then if you get finite generation modules and choose generators and integration by finite dimensional spaces. And associated gradient module is a gradient module over a commutative ring. And then you can use the usual picture from algebraic geometry. You get gradient module of gradient ring. Then you get J invariant support, which is a conical coisotropic variety in affine space. And this choice of generators for general variety of affine space, nobody really does it. What people do, in general case, for smooth affine variety, you make a different filtration of differential by infinite dimensional subspaces. Namely, take filtration only by degree along differential operators, only by degree d. And then again, associated gradient algebra is commutative, and you get conical coisotropic subset of potential bubble. Now it's conical with respect to dilation of fibers of projection. So my goal is to describe some support which doesn't depend on choices. Like for the potential bubble, I want to forget that it's potential bubble. So it claims that this one can has a full picture. So let's start with potential bubble. We have a category of holonomic d-modules. And this category of holonomic d-modules is something remarkable. Also, although the varieties are fine, the x groups are finite dimensional. And it's and you get only x group with finite dimensions. You can also define a non-affine variety by doing pieces. And then come on up to twice dimensional chemical. Then I can, for any two, consider K0 as a multiplicative of holonomic modules, and there's a Euler pairing. Consider alternating some dimensional x groups. It's nice pairing, but it has a little pathology. This K group was assumed, but this form has infinite rank, and we are multiples if you use that. So the question how to write a formula for this thing. It's a logical formula, like have some kind of like chain classes. In this complete trinity, it's a bit ugly. And what I claim that this category is just exhausted collision of some full subcategories. Somehow this inequality less than to sigma bound support by something, which I explained And this sigma belongs to some filtered partial ordered set of universal support. And for each, if you this bounded support, this form has finite rank and can write a Colossian formula, like intersection number of two cycles. Yeah, actually, this characteristic is also has some funny property. I don't know whether you note it's symmetric, which is a category, it's not a collaborative category. X groups are not grouped like just, but the characteristic is symmetric. This carbon-electric situation by Lagrangian. And in irregular cases, it's actually wasn't really observed. Yeah, so this. So we have kind of like, when we have controlled part of the category, then to the heart of the structure of some very nice triangulated category, and this triangulated category is the best possible you want to have finiteness in non-negative geometry. Namely, you can see the what's called saturated category, or saturated category is a category generated by one objects. And such that it's realizable in both sense, the left and right. So the form group, so total form space from object to itself is finite dimensional space, compact, and algebra of endomorphism is projected perfect complex of is binomial. It's analog smoothness. Yeah, so we have kind of analog smooth projective variety, and then the smooth projective variety you can consider some perfect objects. You can see geometrically it's generated category of shoes supported to some closed subset, and then take right direct problem. So we can try to see what perfect complex and smooth projective variety whose support doesn't intersect some closed subset. And such category is also called finite type. I give particular class of categories of finite type to it's really kind of the best analog of smooth varieties of finite type we can have in the range. And remarkably, for such subcategories have specific Riemann-Hilbert correspondence, and on the 20 sides you get a category of the same nature. So finite dimensional representation of finite dimensional manifold can be described as a certain differential multiplication. Okay, so what does this mysterious simple sigma? It will be subset of some another set which will describe explicitly. It's some divisors of infinity associated to the symplectic manifold. You can define for any symplectic manifold, namely algebraic symplectic manifold, to consider all possible partial multiplication. M prime, it's a smooth manifold containing M, such as complement is smoothly reducible divisor, and such as local coordinates divisors given by equation x1 equal to 0. The complement is your manifold, and the form has a special form. One term. It's called divisor. And consider divisors as valuations on field of rational functions. So you have different, you can remove little bit from this divisor at the same point. And in the case of dimension 1, the set is when you get a curve, compact and compact. This set is a set of possible irregular terms from meromorphic connections. So if you have meromorphic connection, write this solution at some point. The local solution will formally have some exponential term. You get negative rational powers of local coordinate, like minus square root, or whatever, some coefficients. And then multiply by some formal, at least formal definition by regular connection. Yeah, let's say this is all possible irregular term, except irregular term, but its font is empty, but points at 0 is outside of x. And the sequence will be arbitrary finite subset of it. Yeah, so that's simple one-dimensional case. And in arbitrary case, partial multiplications with many divisors up to n dimension, intersected with normal crossing, instead of intersection linearly connected, and then you choose any of R. For all points of intersection of divisors, all devices, the formula looks exactly like the previous one, but you have several terms of x over xi, xi equations of devices, plus some random one. And if you get such partial multiplications, then you get rational points in a minus one dimensional simplex in the previous set, namely an intersection of k devices, you start to make blob at their intersections. Even if you have two devices, you get something like Fourier fractions, you get eventually rational numbers between 0 and 1, and you get these rational points in the simplex. And if you make this blob, you will have some ratio the same way. And the sets that you comprise this good subcategories are arbitrary finite unions of these rational simplices. Yeah, so it's should really get very stupid situation, you get a huge set that gets a finite unions of simplices. And then intrinsically, this set is split rational points of compact piecewise linear space depending over rational numbers of dimension, was dimension, if you have half dimensions, like manifolds minus 1. But the goal of this thing is story was not only to have B modules, but some other situations like one chloride, few different derivatives. Suppose we have two invertible generators, or some outputs of Q, and the changes x commute, changes y commute, and y and x commute up to multiplication by Q, this is inside. And now I assume that Q is not a root of 1. So this is, you see, it's a transcendental element of the parameter. Then at least this literally standard strategy to define support doesn't work because it considers associative results that are still non-commutative. But one can phrase, give a definition, what does it mean that your module touches this point of the set, or at least which I described previously, the arbitrary symplectic manifold. And here's the picture the following. Here is a nice associative symplectic manifold is a torus, it's commutative torus, it's logarithmic form. And the set, sigma infinity, which I considered before, is very simple. It's a set of rational arrays in two-dimensional rational vector space. And supports are sets of arrays in rational polyhedral Lagrangian form. Now one formulates the notion that module touches intersectional devices. Yeah, these intersectional devices are Poisson manifolds, and one can try to extend the module to this Poisson manifold and try to see whether it's get the negative part of the battery. So let's give you just one example. It will be just in case of one variable. So modulus of one torus is called Q difference equation. Consider this the most classical function in Q analysis, so quantum exponents or quantum dialog or whatever. And it's infinite product or infinite sum, and it satisfies this Q difference equation. F of x is the one set f of x, and we can write f of x as the actual operator y, multiplication by x will be the operator big X, and we see that it's still by this operator, we have corresponding right side module, and what is supported? It's supported 3 rays. So it's kind of like basic things, then we have differential very interesting story what is really Hilbert correspondence for two different situations. When it is the case of one variable, so when you find a collection of rays, what you do, the picture is the following. And suppose absolute value is less than 1. What you associate to is the following object. You get coherent shift on elliptic curve, this is started by cubic power 3. And in two filtrations, such an associated gradient terms are semi-stable with some certain slopes, and slopes are exactly this direction of the space. Yeah, so it's not just a pure game, it helps to formulate human beings. Yeah. Also, one can this interesting question when you consider operators depending on small parameters, what is Riemann Hilbert response in this case? It was a pretty important subject. Yeah, first of all, if you have complex analytic symplectic manifold, you have a canonical shift of abelian categories, which is locally equivalent to a shift of finite geometric modulus on algebras. And algebras are the following type. You consider open Stein-Lagrangian coordinate space, consider algebra analytic functions, and then take series with the various functions and functions. And here you can make the following start point. You write this infinite sum which converges abically, and what you try to think is this variable y are secretly h bar over dx. So you can write the function of x, the function h bar over dx. And both sides in the story you get extend 16 polynomial non-linear functions. Series in h bar. And then if you have possibly close analytic sets, yeah, first you consider such models and some dimensional support will be again at least half of the dimensions of the manifolds. You call holonomic models, for instance, dimensions half, but then you mod out by h torsion part. And then we get category linear or Laurent series ring bar, and it's a sort of arbitrary closed analytic subset. And the question is it equivalent to some kind of representation of a number group of various complexes? In some simple cases, yes, but in general, no. And again, it's very easy exercise done by Shubhara that even when your right is smooth, you can consider modulus which are locally isomorphic to find some unique non-trivial simple object. Like varieties given by y equal to 0, it's the functions on x and series in h bar. And this category will be essentially representation of a fundamental group depending on small parameter h bar. And this is regular models for this variety. But there are other models which support an L, even on this variety, and get not tricky situation. So this category is kind of infinitely complicated, similar like all holonomic models, when we don't specify support at all, in the case where there's no parameter. And actually, this concept when we worked last year some kind of generalization of Riemann Hilbert correspondence for arbitrary symplectic manifolds, and this was part of the theme was to kind of to specify the supports and get more reasonable categories. And we found a correct language description for what is can support. It's not just Lagrangian, it's some more fine data. In the case of small parameter, and this description is very similar to what I have in absolute situation. We have no small parameter. Maybe I multiply my manifold by a line corresponding to Planck constant. It will be Boston variety, so you get Boston bracket. So this will get a family of copies of your manifold, which are not equal to 0 symplectic leaves, but 0 to degenerate commutative situation. And now one can try to start to move blocks, smooth vector surface, or maybe we can go to roots of one constant, and then get some set of divisors on which have been collapsed, so that this Poisson structure extends to non-singular structure. In general, make one Poisson structure can have poles, it has no pole, and it has no zero on your divisor, and you get reducing vector. And this set of symplectic will be analog of this C infinity, and again, general support will be a piecewise linear subspace, compact piecewise linear subspace of dimension constant, and we were able to formulate a local and proof ring response in the case of chemical one in a dimension. At least we have language to formulate. And this enhanced supports should be used in asymptotic analysis. This usual this creative operators, so the functions of exponents of some function divided by h bar plus have like a series in h bar. But when we make direct images in some kind of non-degenerate, you usually get expression of the same nature. But if something is not generic, you can land with something more complicated. You get exponent, but now you get something like square root of h bar, square root of h bar, various things. And this is how it can support and quote exactly this irregular terms which can appear in direct images. So before I told you that the support is piecewise linear space, and maybe I'll just give you some kind of mental picture which I have. What really goes on. Suppose my symplectic manifold is dimension 2. Then, if you get kind of some Poisson multiplication, you can get maybe it's what I mean here is this picture is small parameter. I make some block and I get in special fiber several symplectic leaves where my module ends. And these leaves have kind of lines of contact. Lines of contact will be a fine line C, and belong to symplectic devices attached to each other. And the support will be some kind of undetermined object in symplectic part. You cannot really specify what is the but you know when it's touch the boundary, and which touch the boundary is reaching up to the situation, the boundary. So this dark red points are well-defined points of my mental picture, and this, what is between it, it's a fuzzy part. And the corresponding graph here, this piecewise linear space is just one point for each divisor, and you get intervals, factor with all rational points and constructing blobs. So you get this piecewise linear budget. And what is going on? The supports, we have two situations without small parameter or with small parameter. It supports with compact piecewise linear sets. Subsets of something. And then he made some notion of skeleton which appeared in context of mirror symmetry. You can see that not symplectic manifolds but Calabi varieties, varieties volume element of a non-archimedean field. And in the case when varieties generates maximum, this will be well-defined closed subset skeleton of recurrent spectrum, and the skeleton will be defined is the same space, but cell decomposition depends on the model, but intrinsically it's a linear object, and maybe just a little remark, it's really it's a linear object. For example, consider like P3 star two-dimensional sphere. But then the basic surface can have huge group of symmetry, like SO118Z. When the length is SO118Z acts on two-dimensional sphere, like this is linear transformation symmetry equations, which is very hard to imagine how this group of symmetries of high-dimensional hyperbolic space acts on this little two-dimensional sphere. This picture. Yeah, so this Berkovich spectrum in non-archimedean geometry is the following. You have some kind of time domain, you get coordinate space, you get system of equations and inequalities, it's a norm for some function less than 1. Then I get algebra functions, and then I consider multiplicative semi-norm for this algebra functions that form locally compact space, causal space. So it's very close to native intuition. It's better than original date picture. And that here is said as polygons in this big space. Yeah, so this set of in case of star product, when I consider small parameter, this set of devices which I had consider all my supports, it contains points corresponding to various things. Points corresponding to maybe single or irreducible Lagrangian subvariety of your manifold. Namely, what you do, you have, let's suppose you have smooth variety, because the A corresponding to this variety, take you up, and very easy calculation shows that the session device is spectral. So the tangent bounded to the set. But then we get six of points of a different nature, which don't correspond to Lagrangian varieties, to something smaller, like isotropic varieties of points. But if you look more carefully, it corresponds to generic points of products of, for example, we can take products of polydisks. You consider like again in coordinate space, you consider pairs of points, it will be Lorentz series and Planck constant. And consider two points whose norms are less than R1 or R2, which is some relation of 6. So the product of this guy is 1. What could be less than 1? And what does this number 1 remind me? It reminds me of this picture from the object start. I start this ellipsis, and ellipsis of area 1. So you have kind of a horizontal size times vertical size 1. And so this coherent state from quantum mechanics has analogs on this non-archimedean nodes. And it seems that they correspond to multiplicative semi-norms less algebra differential operators. And this thing seems to work perfectly well in arithmetic situation. Consider periodic numbers. For example, consider polynomial differential operators in subvarieties with rational conditions. And consider now multiplicative semi-norms of this algebra. So that on constant gives periodic norm. But now this constant 1 and this polydisk will be also give such norm, but we replace norm 1 by p to power 1 minus p minus 1. Yeah, that's the only difference. And then we get definitely something, and my hope is that one can have kind of rough geometric picture for supports and all the various quantum algebras. Yeah, and now the last part. It's very speculative. It's about the risk spectrum. So the holonomic models are nice object, but it's kind of really diffusion from algebraic point of view. It's like object of smallest possible dimensions. Like if you forget it, in case like is it just coherent shifts, the smallest possible dimension will be 0 on the models. And we consider shift is 0-dimensional subvoid, which is idiotic category in a sense. Yeah, it's direct sum of all points. Categories. Yeah, so the very caricature representation of this holonomic model, so here it shows this Lagrangian support. See, it's kind of small spot. Let's try to find analog full heuristic spectrum for all category coherent here, find the D-modules. Again, caricatures with always appropriate part of the heuristic spectrum. You can remove all points of which are not always appropriate, but it's still part of reality. Yeah, so the story is called, but can't really make analog of localizations. There is something good about algebra differential bridges. It has a property. Each right fraction equal to some left fraction. So it means that it can make define skew field of fraction and you have more or less canonical form and of the element. But localization do not look work as we used to in this conventional case. And so the basic pathological example is the following. Consider differential bridges in one variable, and if you invert variable x, element x is the differential bridges on Gm, finite minus 1. If you remove the x, it's by Fourier transform the system. But if you invert both of them together, you get algebra of exponential growth. So it's x minus 1, bx minus 1 will be considered almost a process of the linear dependent. And so what here goes on? And here positive characteristic seems to come to rest and gives a picture how to view what will function. This is utilizations. Yeah, so yeah, first of all, I recall this properties as local support. Whatever B models have dimension, this dimension of a manifold, in the case the characteristic is 0. But if the characteristic is positive, it's totally wrong. Because in this case, the algebra differential bridges will have a huge sample. Let's consider, like, again, preliminary case of affine space. Consider polynomial differential operators. And now suppose my root is over Z mod P, so P times identity is equal to 0. And then the sum has a huge sample. These power generators will be sample elements. And the algebra will add to my algebra run P to power m, so twisting form of matrix algebra. And then if you get such gadgets, it's a zero of the risk spectrum works as well as for commutative algebra. It's small finite dimensional matrix algebra. It's fibers. Okay, so we have this very simple picture, and suppose now we have R is one over integers, so it's and we have some non-zero element in this algebra. Then we make reduction modulo any prime number. Get element of the algebra of this coefficients R of B. And yes, essentially it's matrix unit function of two-dimensional affine space. And then it's vertical outside, exactly outside the locus and the geometries. It's not vanishes. And the geometry is a common surface given by some equation, which is called P support of cyclic model. In general, we have holonomic model, which is not holonomic, we have quantitative model, we make generators, we make reduction, and suddenly you have P support for HP, subset of affine space, subschema of affine space. But now, the dependence of the scattering surface on prime numbers is typically chaotic. First of all, the degree of the scattering surface grows with P. Each part is P to power n minus 1. It's very easy calculation. No, so it's a kind of interesting scheme. And as one, it doesn't grow. So you have plain curve of the same degree for each P. But it stays constant, but the curve kind of like moves chaotically with prime numbers. is already very interesting in case n equal 1. I have a conjecture that this things correspond to material exponential mnemonics, something essentially comes from Lagrangian, now with irregular singulariety. And in high dimensions, it's something which I don't understand completely. At least it contains all linear functions or some squares, like Laplace operator, and reasonable operators. It's the definition of reasonable operator. Case of Lagrangian. It looks as this operators essentially come from some kind of integrable system, some Hitchin integrable system. Maybe I have confusion, some understanding of them. But at least linear operators is already a good case to start. And now we can see the complements to these hypersurfaces, which are completely well defined for these nice operators. It looks like it's very reasonable that one can make a localization of wave algebra by adding all operators with the respective symbol to this guy. So different operators can have the same symbol. Yeah, the simplest example is something like x over dx minus rational number. And for any rational number, we get coordinate cross. Yeah, so it's something which is impossible to work with by definition. But it proves that we go to like mutual product, we get to non-archimedean. Maybe this, at least for this